All right, welcome back, folks. So, last time we were talking about the Lorenz system, and in particular, we were talking about some interesting behavior that we see on volume zero subsets of the phase space. We found an object that we deemed to be a strange attractor, so something that wants to pull solutions in toward it, but the dynamics on that set were we outlined them as being chaotic. So it's in general actually very hard to prove that something is chaotic. Right? There's lots of indicators to show that you might suspect chaos, but actually showing that something is the dynamics on a certain subset are chaotic is very difficult to show in practice. So what we would like to do is find a way to ease that analysis to make it a little clearer as to when systems show chaotic dynamics, and specifically on certain subsets, much like the Lorenz system on the Lorenz butterfly. So we are essentially trying to track all the different ways that a system could be chaotic, and frankly, over the past 50 years, our analysis has been really, really intense, but has only produced really 4 unique ways that we can actually see chaotic dynamics. And these are what are known as the routes to chaos, or the routes to chaos, depending on which region you are from. So some of the routes we've already seen before. So we saw back in Logistic Map that there was this period doubling cascade effect. Now, we didn't actually explore it too far, but there is kind of a uniform way that periods double, and this is based on something called the Feigenbaum constant. So Feigenbaum actually literally translates to fig tree in German, which is hilarious because the logistic map kind of looks like a fig tree, or the bifurcation diagram looks like a fig tree. So, this guy he was born to do dynamics, chaos. So, just to let you know, there is such a thing as the Feigenbaum constant. It tells you the natural ratio of when you can expect period doublings to occur in that cascade. And we saw it. We saw the period doubling effects. We saw that crazy fractal looking bifurcation diagram. And that was one way that we kind of indicated that chaos existed within that system. Second, we didn't really say anything about it, but we did observe it in the Lorenz system, that there is this idea of intermittency in the chaos, that solutions like to bounce around quite a bit in these chaotic systems, like the Lorenz system. Solutions like to bounce around, but they do constantly come back to these nice near fixed point solutions. So it's, I could probably just find this in our textbook. So let me bring that up. So as I'm talking about it, so don't mind this stuff here, and I want that textbook, and I can backtrack it a little bit here. Hum. Where are you? That's there. Okay, period doubling, intermittency. There we go. So notice what's really happening here. When we get close to a fixed point solution, our solutions like to look regular for a little bit. They like to slow down and then be chaotic and then slow down and then be chaotic some more. So this is the idea of intermittent chaos, that these guys are trying to home in around a fixed point of some iteration of our map. So in this case, Strogatz looks at the period 3 orbits and says, okay, sure, this guy starts to look like a period 3 orbit initially, but then he kind of bounces out of it and becomes a chaotic solution, but then it starts to come back to that period 3 orbit. And that's the idea of intermittency, that our solutions look like they want to home in on periodic solutions, but then they turn into chaotic solutions because they get sent through that fixed point in the iteration of the F3 map, as it were. So that's another route to chaos. So when we see intermittency, we know that chaos exists within the system. Same thing with something called a crisis. And this is something that we will discuss very briefly toward the end, right? When we talk about chaotic folding and the Smale horseshoe, we will get to what's known as the Henon map, and that's what this example is down here. That Henon map is one example of it exhibits what's called a crisis, or a chaotic crisis. And I love the names for these things. Everybody's just so into it. Like they're like really sci-fi names back in the 70s. Like everybody was just jumping on the chaos bandwagon. We got stuff like the butterfly effect and crisis and chaos. Oh, it's just so many great dramatic names, and the media jumped all over it because it seemed like, oh my God, there's crisis in math. Oh no, guys, we just discovered something that was maybe a little counterintuitive. So it's best not to blow things out of proportion until you're sure you have something new, and we actually do. There is a fourth known route to chaos, and this is the Ruel-Tockens-Newhouse route to chaos. And it has to do with higher dimensional systems. So right now, we're not going to worry too much about it because chaos is already tough enough to deal with as it is. So we're going to try to nail down some fundamentals before we move into anything higher, right? And this fourth route to chaos is most easily seen in kind of the three-dimensional analog of our quasi-periodicity examples from the couple oscillator a couple of videos ago. But we'll leave it there for right now. There is a fourth route that we know about, and all four of these guys have actually been observed in physical systems. So they're not just mathematical idle curiosities. They actually have been observed in physical systems. And unfortunately, for the past 50 years, this is all we have to show for chaos. There's really not a whole lot that we know about it. So this is still a very active field of research, just figuring out what are the routes to chaos. Is there a complete list of all the routes? Or is there a distinction between being a mathematical route to chaos versus a physical route to chaos? There are lots of different things, lots of questions that we still don't know the answers to. So what we'd like to do is make sure that we get a good fundamental idea of what these routes look like and why our list is so small. These are really, really complex systems, and showing rigorously that they are chaotic is not easy. So one of the easiest things that we can do for ourselves is bring ourselves back to the fundamental, back in like the 60s and 70s, late 60s and early 70s. The idea behind what people were studying and what drove them to look for chaos in these particular examples. And we were just looking for really simple things, really simple dynamics that could exhibit very complex behaviors. And a lot of the time, the crisis route actually occurs in folding maps. Okay, so we have talked about period doubling, we've seen intermittency, and now we would like to go ahead and see where crises occur. And they most often occur in folding maps. And maybe the most prominent example here is what's known as the Smale horseshoe, which is effectively just making croissants or anything where it's like a puff pastry dough, where you are folding something over and over and over again in a very specific way. And not only do we see it in this contrived Smale horseshoe, we see this in something called the Rossler system, which is very, very closely related to the Lorentz system. But we notice that there's this nice folding and doubling that keeps occurring as we continue around and around on that map. And we also see what's known as the Henon attractor. Right, this is a sort of boomerang-looking map, but it's also going to fall under that regime of folding, that we're just going to iterate folding something over and over and over. Right, so this top one, Smale's horseshoe, is kind of one that falls into that realm of mathematical curiosity or mathematical idle curiosity, but the Rossler system and the Henon map actually do show up as describing these kinds of systems. The Rossler system showing up as part of the Lorentz system in a certain regime or a certain simplification, and the Henon map is actually putting numbers to the Smale horseshoe. It's making it a rigorous discrete map. Ready rigorously, explicitly defined discrete map. But these guys are very, very difficult. It is difficult to write down the specific dynamics. So what we would like to do is find a comparable system that is easier to study. Ideally, we would like to show that these systems are exactly the same as something that is much easier to study. And just because it is easier to study doesn't mean it is easy to study, just easier to study. So to illustrate that point, let me go ahead and point your attention back to the logistic map. But what we did in our work earlier in the semester is we restricted ourselves to the parameter range where R was between 0 and 4. What we would like to do now is actually break past that. So let's go ahead and take our parameter R to be greater than 4. Right, and what happens here? This means that our parabola, right, the image of this guy, the image of our map, the graph of our logistic map, has part of the parabola poking over the line xn plus 1 equals 1. Now this is important because if anything sitting in this interval, what I'm calling A, if anything gets mapped up here, then our cobweb is going to, well, let me see where our cobweb is. Cobweb's going to be roughly here. Cobweb is going to immediately throw that guy outside of the 0 to 1 interval. This is actually the primary reason some students were asking why we only considered the interval from 0 to 1 before, and it's because of this, exactly this fact, that when R is less than or equal to 4, then this interval from 0 to 1 is it is invariant, right? Things do not want to leave, solutions do not want to leave the interval from 0 to 1 once they start there. So making sure that R is greater than 4 makes it so that there are solutions that can escape that interval from 0 to 1. And this is what we want to show, that if we tried to run this numerically, our argument before was that, well, okay, it looks like everything is unstable when R is greater than 4. But we know that's not quite right, because the computer will not track anything unstable, and it will not track things of measure 0, not unless you have a robust algorithm that seeks them. So what we would like to do in this in the following exposition is show that there actually is an invariant subset living inside this interval from 0 to 1 when R is greater than 4. The problem is that it has measure 0, right? It has no length associated with it, so the computer will not find it, not unless you are explicitly looking for it, and that takes a fair bit of analysis just to make sure your algorithm is robust enough to find that set in the first place. So in this parameter regime, numerical simulation thinks that solutions all get tossed away and they all blow up to negative infinity. But there is an invariant set in here, and we're going to show that the dynamics on that set are chaotic. But again, this is actually really hard to show explicitly using the logistic map. So what we would like to do is pass the problem into a different phase space, something where we can analyze the dynamics on a different object and then see what happens. See if we can study it a little more easily there. So in this case, let's establish this rigorously, that because R is bigger than 4, there are exactly two locations where this parabola is going to intersect the line xn plus 1 is equal to 1. Okay, if we track those back, get the pre-image of those points, then there are 2 points, x plus and x minus, given by these two values here. Right, and you can solve that with a plain old quadratic formula to see exactly where those points are. But the vertex of the parabola now extends past this horizontal line at 1, and the orbits that live within this open interval from x minus to x plus must all escape the interval from 0 to 1. However, the points that live in the interval and are not in A0 are still mapped within 0 to 1 because, well, their heights all stay between 0 and 1 on the xn plus 1 axis. So what we wind up creating here are, well, there's going to be two sets here. Do I want A1? Yeah, we'll talk about A1 in a second. So there are two sets. There's an I0 and an I1. Okay, so in this case, right here, this is I0 and this is I1. These are the remaining two intervals, right? If I color them in, it's this guy and this guy. These are the intervals that remain when we remove A0 from the closed interval from 0 to 1. All right? So, who cares? Well, frankly, I do. Because look what we can do here. If we pull back the map, right? The thing about this map about the logistic map on these intervals is that it's invertible. That I can go ahead and pull back to one of these two sets, right? To anything that lives at a particular height has a preimage that belongs either to I0 or I1. And if I go back further, I can go ahead and divide this interval up into more pieces. I can say, okay, let's see what happens if I pull this guy back 2 iterations. Well, I'm going to follow this blue line down and then back to see where it ends up over here. And that makes an even smaller interval on the far left, and it makes another one over here on the right. And those are two new intervals. Those are the two pre-images that are associated with this left-hand side, right, the I0 interval. And I get something similar on the right side, where I get an I10 and I11 sitting inside of I1. But the point is that I can keep following this map backwards and further back and back and back and back until I wind up with a set that I'm going to call lambda sub n. And this is essentially just going to be all of the all the values in the interval from 0 to 1, such that the nth iteration still lives in 0 to 1. So in this case, it's a consolidation of everything that's just happened upstairs. We are removing more and more open intervals that are part of the escape regions, right? Where eventually the value in that any value in that A0 or A1 interval is going to eventually be mapped outside of the interval from 0 to 1. So lambda n here is tracking which points stay within the interval from 0 to 1 after n iterations. And then we have a limiting object where we don't have a cutoff, that there are points that live within this interval from 0 to 1 that never escape the interval. And we're going to call that set lambda. Okay. The goal here is to show that the logistic map is actually chaotic on that set lambda. But it's hard to show that with the logistic map itself. So what we are going to do is try to identify the points in lambda with some other space, some other phase space. And we're going to introduce a certain naming scheme. So points in lambda can be identified with sequences. And in particular, they can be identified with binary sequences. Now let me tell you how this works. Suppose that we had a set, suppose that we had, say, a fixed point here. Right, the fixed point is 0. We're going to identify that guy with the sequence of zeros. Why? Because if I keep pulling that image back, well, 0 keeps living further and further. If I keep mapping this guy further and further back, it's always going to stay on the I0 side of this middle interval A0 that we are omitting. Okay, so this guy, the zeros are always going to correspond to the left interval, whereas the ones are always going to correspond to the right. So our fixed point, our non-trivial fixed point that intersects the xn plus 1 equals x line, or xn line, this guy always stays over here. always stays on the right side. So we're going to say it stays on the I1 side. So we're going to say after one back iteration, there's 1. After 2, it's still on the one side. After 3, there's still on the one side, and so on. Now, something that's maybe a little trickier to see, you can actually go ahead and find this with MATLAB, and we can do that real quick. Let me see if I can't bring that up. MATLAB, where'd you go? Where did you go? Oh, come on. There you are. MATLAB. And then we'll bring up the notes, put them over here. So here's the deal. Let's see, what's the name of my function here? File, yeah, go ahead, reconnect, because you're silly like that. It keeps signing me out. I'm telling you, I always do this. I always set it up where MATLAB is open and connected before I start the videos, but it always signs out after about 5 minutes or so. So anyway, that's what it's called, the cobweb diagram. That's right. So what we're going to go ahead and do here is we are going to create a function using an R value of about 4.3. And f, we're going to make the function handle r times x dot star 1 minus x. So there's my function handle. And I'm going to figure out where this guy has period 2 orbits. And the way I can do that is say f of, we're going to make a new function handle in here, f of x minus x. We're looking for the zeros of this guy, because if this function is 0, that means that x is a fixed point of the f2 map. And we're going to say, okay, that happens somewhere near about 0.5. Okay, great. So about 0.311111. And we're going to go ahead and say that this is c equals answer. And I can go ahead and see f of c is equal to that, f of answer. And it comes back, and it cycles. So this is a 2 cycle. So 0.3111, yeah, 3111 is part of a 2 cycle, whose other member is about 0.291, wow, 9215. And that's exactly what we see in the notes here. Oh, come on. Right? So that's exactly what I'm saying, is that there is a 2 cycle in here, right here. And these guys, the points belonging to that 2 cycle, are encoded as either 0101 repeating or 1010 repeating. Why? Because 0.311 starts right about here and then keeps flopping back and forth here, and then back here, and then back here, and then back here. So we start on the I0 side, then go to the I1, then the I0, the I1, the I0, and it keeps flopping back and forth. And similarly, if we start on the I1 side with the 0.9215, then we start on the right side, and then we go back. And then we start, and we go back on the right side, and then we go back. So it flips back and forth between the 1 and the 0 side. But the point is, each point in this lambda set can be identified with such a sequence, which tells us which side of A0 it lands on at a given iteration of the map. And such a sequence is going to be called the itinerary of that point. Right, we're just going to name it the itinerary. Right, you could call it the orbit, but whatever, it's the image. Yeah, well, technically, no, it's not the orbit, because that no longer lives in lambda. So the orbit is not going to stay in, the orbit stays in lambda, but we are mapping lambda into sigma, which is going to be the set of binary sequences. Yep. So sigma equals the set of binary sequences. There we go. And binary sequences are just going to be, yeah, zeros and ones, mapped from starting at a 0 index, and then going to a 1, a 2, a 3, a 4, all the way out to infinity, what have you. Okay? So what we would like to do is show that lambda, this weird set that lives inside of our interval from 0 to 1, which is tracking the non-escaping points of the logistic map, is actually homeomorphic to the set of binary sequences, which is bizarre. Honestly, yes. For lambda lives inside of the real line. So there's an induced metric. There's an induced way of measuring how far apart points are in lambda by measuring how far apart they are on the real line itself. But the question now is, how do you measure how far apart two sequences are? Right? If you've seen my Math 145, my applied linear algebra class, then you'll know exactly how we deal with this. We're going to go ahead and create a metric space. We're going to create technically a normed space, but this one is just a plain up, a straight, no, sorry, not a normed space because that implies linearity. This is a metric space. So in order to establish this homeomorphism, I need to know what open sets look like. I need to know what open intervals look like. And that question is very strange in the sense of what does it look like for sequences to belong to an open set? That is weird. Okay, that is something that we need to deal with. So, let me see, how long is the video running? Yeah, we're gonna keep going. Let's see if we can't establish that metric, and then we'll see about showing how to apply it. So, to establish the homeomorphism, right, the conjugacy between lambda, our non-escaping points, and the set of binary sequences, we need to come up with this notion of distance. And the general concept here is that of a metric. Okay, and metrics satisfy three properties, well, four. First, this guy is a function. It takes in two elements and then spits out a number r, a real number r, that is going to effectively tell us the distance between those 2 points that we fed the function. So, I mean, you're probably most familiar with seeing the absolute value of x minus y. This is the distance between x and y, and this would be in r, so if I wanted the distance between 1 and 7, this is the absolute value of 1 minus 7, which is the absolute value of negative 6, which is 6. Right? So that there is a distance of 6 between the points 1 and 7 on the real line. What a metric does is it extends that idea, and it says, okay, what are the key axiomatic properties that I need to have in a notion of a distance? So first of all, the most obvious thing, distances can't be negative, right? So specifically, this function has to be non-negative. And in particular, the only way that we're going to get a zero distance is if we're measuring from one point to the same point. So we don't want there to be some non-zero distance. We don't want to say that, okay, where I am here in Sacramento is a distance of 0 away from, say, Paris. No, that's insane. We don't want that. The only way that we're going to get a distance of 0 is if I'm measuring from one point to itself. Second, from measuring from where I am to where Paris is should be the same as if Paris measures where they are compared to where I am. So I should get the same distance measuring from S to T as I get from measuring from D to S. And that'll be for everything sitting inside this set of sequences. And finally, we need something that mimics the triangle inequality. Right? This is effectively what most of analysis hinges on, is this structure of bounding arguments. And one of the strongest ones, most important ones we absolutely need in order to proceed is the triangle inequality. And it just says that detours are slower. Or, yeah, detours are slower. So from S to U to T, it is actually, so the distance from S to T is shorter than the distance from S to U and then from U to T for any triple S, T, and U. So triangle inequality still holds here. Great. But it's maybe a little tricky to see how we can come up with a metric at all on the set of binary sequences. Right? This guy doesn't get a naturally induced metric, just like we were able to on the set lambda, just by looking at what the metrics look like on R or Rn for any Euclidean space. So what we'd like to do is actually construct this metric explicitly. And the way we're going to do that is we're going to make direct comparisons between the members of the sequence and then scale them down. Right? So what we're doing here is saying that the distance between two sequences is going to be the absolute value between of the difference between each individual component-wise entries, so S0 minus T0, S1 minus T1, S2 minus T2, and so on. But each time that we take this difference, we're going to scale it down by a factor, an extra factor of 2, starting at 2 to the 0. So to give you an idea of what this metric looks like, consider measuring the distance between our 2 points. The fixed point at the origin, so this is what we identified with x equals 0 in the logistic map, so on the set lambda. And then we have this guy, which was one of our period 2 orbits, so this was effectively about 0.9215. So this would be where these guys map inside of the set of binary sequences. So these two locations on lambda are a distance of about 0.9215 apart, but if we map them into the set of sequences with this particular metric, then we actually notice that these guys are only ever different on the odd components. So technically I did that wrong, so let's fix it now. So this should be, yeah, they are different here, so that's a 1, the half, the quarter slot, the eighth, the 16th slot, and so on. So this will actually be the sum of quarters. And this will just be, what is it, 4/3? Yeah, so 1 over 1 minus a quarter is 1 over 3/4, so it's 4/3. So this will be the distance between these two sequences in sigma, the way we've defined it here. Now, this definition of the metric up here, let me actually go ahead and put that in a red box because it is that important. Oh, shoot. Let's see if we can't fix that. There we go. All right. So this guy is our definition of how we're going to measure distance in this space sigma. So notice that this guy does imply that the distance between any 2 points, any 2 sequences in sigma is no more than 2. Because at worst, these guys could differ in every single slot of the sequences. They could be dual to one another. And that would mean that I actually have a distance that's capped off by this Zeno's paradox sum. Right? I keep adding half of the remaining distance here. So I actually wind up with 2 as my upper bound. That's the worst or the largest that any distance could be here. And we can check even further, that this d function that we've defined in the red box satisfies the 3 axioms that we need to be a metric, right? And I'll leave that to the reader or the audience to think about. Maybe we'll talk about it in class about why it satisfies those three properties. But let's go ahead and kill this video. We'll start part 2 in the next one. We're going to start working with this new metric space and say that all the dynamics that we want to see on lambda as a subset of the real numbers, those dynamics actually do transfer over to dynamics in this new metric space. And to see how that works, let's